Imagine you are inside a train moving at an extremely high speed and you turn on a flashlight. From your perspective, the light behaves normally. But here is the strange question. Does the person standing outside the train see the light moving the same way? And even more shocking, do you both experience time in the same way? The answer is no. And this is where one of the greatest revolutions in science begins. Einstein's special relativity theory. In the late 19th century, physics seemed almost complete. Newton's laws explained motion perfectly, and Maxwell's equations explained electricity and magnetism. But there was one big problem: light. Scientists believed in something called the luminiferous ether, an invisible medium through which light waves were supposed to travel, like sound waves traveling through air. To test this idea, scientists performed a famous experiment, the Michelson-Morley experiment. The result was shocking. No evidence of the ether was found. This created a deep crisis in physics. Something fundamental was missing or wrong. In 1905, a young patent clerk named Albert Einstein changed everything. Instead of trying to fix old theories, he took a radical step. He ignored the ether completely. He started from two simple principles. The laws of physics are the same in all inertial frames, objects moving at constant speed. The speed of light in a vacuum is always constant, no matter the motion of the source or observer. These two ideas were enough to completely reshape our understanding of space and time. One of the most shocking consequences in time is time dilation. The faster you move, the slower time passes for you compared to someone who is stationary. So, a person inside a fast-moving spaceship experiences time normally, but someone on Earth would see their time moving slower. Time is not absolute anymore. It depends on motion. Another strange result is length contraction. Objects moving close to the speed of light appear shorter in the direction of motion. This is not because they are physically compressed, but because space itself behaves differently depending on the observer. Things get even more surprising here. Two events that happen at the same time, for one observer, may not happen at the same time for another observer moving differently. In other words, there is no universal now that everyone agrees on. Then comes the most famous equation in physics, E equal mc square. It tells us that mass and energy are interchangeable. A small amount of mass can be converted into a huge amount of energy. This principle is the foundation of nuclear energy. As an object with mass moves faster, it becomes harder to accelerate. As it approaches the speed of light, the required energy becomes extremely large, approaching infinity. That is why no object with mass can reach the speed of light. Imagine two people, one stays on Earth, the other travels in a spaceship at near light speed. Each person feels their own clock is normal, but when they compare results later, they discover something strange. Time passed differently for each of them. Nothing is wrong with the clocks. The nature of time itself is different. Special relativity completely changed physics and our understanding of reality. Before Einstein, we believed time is the same for everyone. Space is fixed. Motion is absolute only in speed. After Einstein, we learned time depends on motion. Space is not fixed. Reality is relative to the observer. It became one of the foundations of modern physics, from particle physics to GPS technology. In conclusion, special relativity is not just a scientific theory, it is a complete redefinition of reality itself. Time and space are not absolute, they are flexible and depend on the observer's motion. And this leaves us with a deep question. If time itself is not fixed, then what does reality really mean? Thanks for watching. See you next time.